This video is going to be a demo of the second order system lab. We'll be using a accelerometer and a cantilevered beam. We'll be trying to characterize the response of the second order system with natural frequency, damping ratio, and time constant. So we're looking at measurement system behavior and using lumped parameter models. So the general idea is that we have a model that looks like this, characterized by second order differential equations or differential equations in general that can be parameterized. Call that lumped parameter modeling. And so we can use the behavior of the measurement system along with the dynamics of this thing that we're actually measuring to understand whether or not our measurements can be accurate for the intended purpose. Generally, we're characterizing measurement systems with an input signal and then an output signal and initial conditions. So we have zero order systems, first order systems, and then the system that includes an inertial component is characterized or considered a second order system because it's got a second derivative in time. In traditional vibration notation, we take those A's, A2, A1, A0, and transform them into zeta, damping ratio, and omega n, natural frequency, along with the sensitivity, K. We can look at this as an impulse response and also as if the input is periodic or any other waveform. During this experiment, we're going to pluck a beam, so it's effectively an impulse response, measure the free vibration, and use characteristics from that to fit up these parameters. Using these equations here, natural frequency, damping ratio, and time constant tau. Okay. So this is for a ice testing rover, and the idea is that we have a system that looks like a little rover with a probe on the end that has a measurement system, and we'll model that as a cantilevered beam, and we want to see how the dynamics of that beam change over time. So we're going to be using a scope, a charge amplifier, an accelerometer, and we'll set up here. We're going to be following the assignment in Chapter 3, and this demo will basically go over the setup more so than following this step by step. During this experiment, you will get the chance to choose different beam lengths and end masses. So there'll be a total of 3 masses and 3 lengths. And that's 9 different test points that you're going to consider. So there will be a component of this that you're going to need to read the textbook, and in particular, under the measurement system section, we're looking at second order systems, and so you can see as we get down to that, this is where the math is derived. Starting right here. Okay, so all the background that you need is going to be in this section of Chapter 3. And again, we're going to be using primarily this equation right here for characterizing the damping as it decays after a free vibration impulse response. And so you also should note that there's some details of an accelerometer in Chapter 12 that are provided. It's essentially modeled as a mass spring damper itself. And then there is an explanation of a charge amplifier found in Chapter 6. You don't really need to know all those details to do this lab, but the components that we're talking about and going to be using, they are referenced here in the textbook. We're not going to design our own accelerometers or our own charge amplifiers. We're just going to use the ones that we have. Okay. The accelerometer that we have is from PCB Electronics, and it has specs that you can find online, including sensitivity, range, frequency response, and even physical properties as well. So the basic setup is going to be best shown if I can get the camera focused on this. So we'll stop sharing here. You can see I may have some components. Here we have a small accelerometer. This is a piezoelectric accelerometer. There's actually a quartz in there. It sits on a little mass that goes up and down on the quartz, and it generates a charge as it's shaken. It has a pretty high G range, and so the accelerometer comes in a little box like this and has some calibration specifications. Here, for example, 9.79 millivolts per G is a sensitivity, along with some other specs. So this accelerometer has a 1032 thread under here. Currently I have a little ball of wax I'm just going to use to adhere the accelerometer to a surface as it's moving up and down. We'll measure that. So the beam that we're going to be using is essentially a yardstick clamped to a table, so it's cantilevered with an accelerometer mounted, and then also a stack of added masses or weights here. Okay, so the accelerometer gets connected through a small coax cable like this to a normal BNC connection to this little guy, which is a battery-powered charge amplifier. So you can check to see if the battery's working by just testing here. When it's in the middle position, it's in normal operation. Over here, it's off. Make sure that you turn it off when you're done with the test so we don't drain the batteries. This BNC gets connected here. This gets mounted to the beam via wax or via a screw. And then we have another BNC cable that we connect to an oscilloscope right here. Okay, so that's the basic hardware equipment. The oscilloscope here is a Keysight oscilloscope, 2-channel. This one's currently set up, and if we bounce the accelerometer, it's the yellow channel there. We actually can see it respond and decay over time. And so one of the main things that we're going to do is capture a waveform like this one, and then we're going to measure the frequency and the amplitudes of successive peaks to get the actual damping ratio. So we'll change mass as we need. We'll measure mass with this little scale here. The mass for the accelerometer is actually provided in the specifications from the owner's manual. And then we'll use functions on the scope to capture data here. So we can actually see that if we look at this green channel here, we can actually set up a sine wave that has different frequencies shown. Actually, we'll just ignore that one for now. Turn off this guy, and we'll focus on the channel here. So this again, run stop, allows us to capture data. This goes up and down to move the waveform up and down on the screen. This knob right here characterizes the voltage smallest increment, divisions per box here, and this is the time adjustment. So if I pluck this, you can see that I can actually capture that waveform. If I change this voltage knob, more voltage per volts per division, it's the same waveform, it just looks bigger, and you can actually see up top here where it shows the number of volts per division. And I can also do the same for capturing the time at different time divisions as well. I can use the cursor functionality, and with that I can go through and pick off voltage peaks. So right now I'm finding a peak here. I'm going to note the amplitude here, 153.92, and then I'll go and find the next peak. It's slightly lower, 147 millivolts, which means it's decay. That decay will be different depending on the length of the beam and the masses of the beam. So the reason this is important is because we have this little rover system here for ice testing. We have a depth gauge right here and a little Arduino. It's going to bounce up and down if we don't be careful about the stiffness and the vibration characteristics of this end beam. So this little ruler here is just our training ground for learning how to characterize second order response of a cantilevered beam. So the scope does have a manual, and that's worth taking a look at. We'll share the screen again and go back to that. So you can see through the course website, there's some additional resources here. The oscilloscope manual, which goes over all the background of how to use a scope. And also, let's go back to this slide deck here. Also shows the basics of how to use an oscilloscope, which is a standard laboratory instrument. So with that, you should be able to run the experiment and capture the damping ratio and time constant of a second order system, a cantilevered beam, for the last part of the Module 3 test. So here you can see the scope, how it works, what it does, and so on. Okay. So familiarize yourself with that, and that's the end of the demo for the second order system.